Hi, my name is Miloš and welcome to Element 14 Presents. Today we'll be talking about what it takes to make a drone. We'll take a look at custom electronics for a drone, we'll take a look at PID controllers, we'll crash the drone a lot, and just maybe we'll get it to take off in the end. Let's go and make a drone. This here is the first drone I made from scratch. It's on Element 14 community and I made it about 4 years ago. It uses 3 Arduino Nanos, one as a flight controller and 2 for the radio link. So both as a transmitter and a receiver, and it actually flew. Here's a quick clip of that. Now, the drone I want to make this time, it's a bit different. So this is the size of the prop of the last drone, and this is the size of the drone that I want to make this time. And how I got to this idea is because I did a project with this little board, which is the Arduino Nikla Vision. It's an extremely powerful little board with an outboard camera, IMU, time of flight sensor. So I thought, that sounds like a perfect board for actually making a drone from scratch, and I got to work with it and see its capabilities in a previous video here that I will link below when I made an ornament robot. So I thought, why not design a PCB that would act as a shield for this Arduino and then make a drone out of that. Let's take a look at the design I want to achieve with this drone. I'm gonna keep the design of the drone rather simple. So in the middle we're gonna have the Arduino Nikla Vision because of the IMU, and to it we're gonna attach the custom PCB as a shield. I want to have this taller part on the PCB because I want it to house the RGB LED as an indicator so it can be seen easily from any angle, and also so it can protect the Nikla Vision in case of any impacts. Besides that, we just have to have the 4 motors and the 3D printed frame. So for the motors I went with the 8520 motors. Those are brushed DC motors, so we're gonna use a MOSFET to control each one of them. I tried my luck with 717 motors, but they just weren't powerful enough. These 8520 motors are the same ones used in the DJI Tello drones. So besides that, we're gonna have the already mentioned Arduino Nikla Vision in the center of the drone. The frame is gonna be 3D printed either out of PLA or PTG. Your choice if you wanna recreate this. We're gonna have the custom PCB, and on the top we're gonna have the RGB LED. Now that you've seen the design, it's time to jump into the PCB section right away. So the PCB is quite simple, it's just a shield for the Arduino Nikla Vision. I have it right here. So essentially it's just connecting all of the pins to the MOSFETs, driving them using PWM, and that's it. So designed them real quick, ordered them, soldered everything, and they just worked the first try, right? Wrong, of course. I didn't do my due diligence, I was going too fast, as that will become the theme of this video, as you will see quite soon. And I didn't check if all pins are PWM capable, and they were not, of course. So I just started soldering wires to try to move what pin is connected to what motor, and then I managed to burn out the onboard regulator on the Arduino Nikla Vision. And as you've seen in the previous clip, that's a rather small board, and I really didn't want to risk killing the whole board because it was still working via USB. So I thought, I'll just redesign a PCB. It's small, it's a one-day design. What could go wrong? More stuff can go wrong apparently, because I again tried to be quick, tried using the components I had laying around, and I thought, I'm just gonna use the 1.5 amp LDO that I have. Nope, it was a 150 milliamp one, so that wasn't strong enough either. But nevertheless, here is the second PCB, and this time I just gave it everything to make it work, and I think I just might. So let's jump into EasyD8 so you can see the electronics, or at least the electronics that work. Time to look at the electronics, or the part of the electronics that actually worked. This is a custom footprint I made for the Nikla Vision, which is essentially just a few headers, and these are all of the connections for it. This time I actually connected the motors to the correct pins. we have the LED connections here on the left, as well as the analog pin for measuring the battery voltage. Besides that, I just added test points to all of the other pins so you can solder on new sensors or whatever you want. So let's go to the power. Here's the regulator that we will not talk about. And this is the boost regulator that steps up the 3.7 volts to 12 volts. And now you may ask, why? So here's the thing, the NickLaVision has pretty limited current that it can output on each of the pins, and you want to be able to switch the MOSFETs on and off really fast to be as efficient as possible. So I need to use a MOSFET driver, and to use a MOSFET driver I need 12 volts. So I just used the boost converter that I had laying around and just configured it so it outputs 12 volts, and this down here is just a simple voltage divider for measuring the battery voltage. Now if we go to the motor drivers, you can see these are the MOSFET drivers I ended up using, and these are the MOSFETs. It's a pretty simple schematic, there's nothing much else to it, so you can, for most microcontrollers and for most not pro-grade applications like this, you can pretty much go without a MOSFET driver and just directly drive the MOSFET, but if you want to drive it as fast as possible, especially using a microcontroller that can't provide that much current on its pins, it's a good thing to use a MOSFET driver like this. Besides that, we have the signalization, which is essentially the two RGB LED diodes that you've seen, where you want to have them at the top, and they are connected together, so I'm just controlling them using 3 MOSFETs for the RG and B channels. Here is how the final PCB looks. This is the bottom side and this is the front side. So a lot of via stitching. The motor connectors are here on the side, as you can see, and the NickLaVision is just at the front. One thing that ended up working really nicely is adding all of the pins down here so that you can easily test the voltage of your boost converter or your LDO that we don't talk about, or easily connect another sensor to the pins. And here is the 3D version of the PCB. As you've just seen, the electronics are rather simple, but we still need a way to send commands to the drone. So usually you do this with a radio transmitter and have a receiver on the drone, but I thought, why not use the Wi-Fi capabilities of the Arduino NickLaVision and use this old joystick that I had laying around. So my idea is to connect this joystick to the PC and send commands using Wi-Fi, sending them over UDP, so we can get the least amount of delay between me moving the joystick and actually the drone receiving those commands. So now I'm going to show you how I interfaced this joystick with Python, and how you can do that with pretty much any other joystick if you want to control your other robotics projects. I got all of the data from the joystick using Python when it's connected to the PC, using the Pygame library, and I use the socket library for the UDP communication. So we just need the IP address of the Arduino and for the UDP port to be configured the same way on both the Arduino and here in Python. So these are some of the commands that I wanted to integrate, but for this minimal version for just taking off, I stuck with having to send the references and angle, the reference angles and power, and also arming and disarming. The rest of the code works through essentially 2 threads. The thread 1, this is that function, gets all of the button presses and axis movements, so as you can see here, and it just maps them to float values with 3 decimal points and packs them into, for example, the joy array, which I then send using the other thread function, this one, where you can, for example, see this function where I send using the UDP IP and port, I send the joystick array over to the Arduino, and that's how I actually updated the references. There's not much else to this code, so these are all of the other things that I want to integrate, but just didn't have a chance yet. If you want to test out this code, you can find it on Element 14 community below, so it's pretty easy to play around here with this code and just configure any type of joystick to work with it. Now if we test it, let's just open the serial monitor here. Now when I move the joystick, you can see that we're receiving some commands, and if we move the throttle, for example, you can see the throttle is at 100%. If you move it down, now it's at 0%, or for example pitch axis to the max, that would be around 33.95. I put the max to be at around 35 degrees, so it's doing the conversion live. So yeah, that's it when it comes to testing the joystick. With the electronics working, with the communication working, there are only two things left. So that's the actual physical body of the drone and the flight controller, or the code that's gonna run on the Arduino. So let's begin with the body. Here are some examples of things that I tried but didn't quite work because they were heavy. So I had to go even lighter, as you will see soon how I designed it in Fusion 360 and printed it out. But let's talk about another thing, and that's what kind of a code do we need to run on the Arduino. So a much easier way to do this, to make any kind of drone, is just to use an open source flight controller. That's what I did for the big drone. I used an open source firmware called MultiV, and it worked great. There are a lot of other options, but for this I didn't just want to go the easy route. I wanted to experiment a little bit and to show you guys how it actually works at the base level. As you will see, it works kinda, yeah. But still, I just wanted to show you some of the basics. So what does the flight controller do? So when you keep the stick straight, and let's say you're at 50% throttle, you want your drone to just be steady like this, and you want all of the angles, so the pitch and roll, to be 0. When you move the stick, let's say fully to the front, and your limit is 30 degrees, what that means is actually you're sending the reference angle to the drone so that it moves like this, so that this angle here is 30 degrees now, and it tries to keep that angle at 30 degrees. What does this do actually? It gives besides the drone, you adjust the with the throttle so the drone doesn't start falling, but you also have a force component that pushes the drone forward, and that's how you actually control the drone. It's a bit different for the yaw axis. For this drone that I made, it's all due to the reaction forces to the motor spinning, so you spin the diagonal motors on one diagonal faster and the other slower, and you get this rotation. Some other drones, besides doing that, they also have slightly tilted motors so they can get faster yaw movements. But how do those controllers work? Now we get into the area called PID controllers. There are other types of controllers as well, but now I'll cover how PIDs work and show you how, with just integrating 3 simple PID controllers, we can actually get this drone to fly. So PID controllers, you've probably heard of them, but if not, let me explain. This won't be like a proper mathematically correct defined explanation. This will be more of an intuitive explanation that you can utilize for this project. So let's begin with the flight controller itself. Let's imagine it just as a box, and as inputs we have the throttle and the reference angles, and as the output we have the motor PWM. So this controller needs to control the pitch axis, roll axis, and yaw axis. Let's, for example, focus on the pitch axis. So we have the reference angle coming here, and let me just draw it out here. We have these 3 boxes that we summarize their output. We have the drone, and we have the IMU measurement, which we use to actually measure our error. So the error is when we take the IMU measurement and subtract it from our reference angle to see how far away we are from the actual angle that we want, or the reference angle. And we have these 3 boxes labeled P, I, and D. That's our PID controller, but what do those letters actually mean? So let's begin with P. P stands for proportional. So that's the proportional controller. What that means is that the controller itself, or the drone, will try increasing the power proportionally to how far it's away from that reference angle. And mathematically we just do that by writing this proportional gain times the error, the ET. Okay, so what about the I? I stands for integral, And the integral doesn't work directly with the ET, but rather works with something called the accumulator. And the accumulator is the error that you summarize during all of that time. And you'll see why that's important later. And for the last letter D, that's for derivative. And that derivative takes care of how fast we change the variable and how fast actually that error changes. So the three parameters that you usually can hear about the gains that you adjust are the proportional, integral, and derivative gains. And the output of the PID controller is gotten by just summarizing the proportional, integral, and derivative like so. But now you may ask, if this is the first time you're seeing this, why? So here's an example. Let's look at this graph where you have a reference angle. So the reference was 0 and we set it to some value x, doesn't matter what. In an ideal world, the drone would follow the pitch axis, for example, would have this kind of step change. It would change from 0 angles to x angles in no time at all. But since we're working with real systems, this is impossible, of course. Why is it impossible? You can't have infinite acceleration. You have some kind of mass that you need to control, and so on. First, let's see what would happen if we just have a P controller. This is something that you can expect with just a P controller. It does work to some sense, but as you can see for the steady state, when it continues, you can see that there is a gap. That kind of gap we can easily solve by adding the I, or the integral part of the controller, and then we get the PI controller. What the PI controller actually does, that error that's constant, as you see in the P controller, it adds up in the accumulator as time moves on, and the system slowly corrects for it. That's why it's called the integral controller. And we can add the derivative controller that can further improve the whole performance of the whole system. But how would we use this on the drone? So we need three PID controllers for the drone. We need the pitch axis, the roll axis, and the yaw axis. Those are three completely different PID controllers. Every single one of them is going to have their own parameters, and in the end, we pretty much just need to summarize them in a particular way. So here is how we're going to do that. This is the labeling of the motors. So for example, if we want to tilt the drone to the front, we need to increase the power in the motors in the back and lower the power in the motors in the front and stuff like that. So let me write out these equations real quick. Oh, I messed up the motor numbering. Okay, this should be correct now. And okay, this is the final set of equations that we're gonna use. And when you look at this, so if you wanna, for example, for the pitch, the motors 1 and 3 are gonna have the same sign before the pitch, or the plus, because they work in tandem for that axis. Just as well, the motors 1 and 2 work in tandem for the roll axis, and motors 1 and 4 for the yaw axis. Now that you've seen how PID controllers work and how we're going to integrate them into our drone, let's write this code so we can actually test this drone out. So I split the code into a couple of files just so it's easier to edit, read, and stuff like that. Here we have the libraries, the pins. This file is for all of the parameters, for example, all of the PID parameters, variables, and stuff like that. The second file is for functions. So for example, the motors function, which takes 4 values, float values that are between 0 and 1, for example, or 0 and 100, and converts that into the analog write signal that we want to use for our motors. Then we have the command. This is just one big function where, depending on the UDP command sent, for example, K0 is the kill all command. That's the command you send when there's an error. So you see that the drone is gonna hit the wall, or it's upside down and you just want to stop all of the motors immediately. You lost connection to the joystick or whatever else. This is that kind of a command. Command 1, this is the case 1. That's, for example, where you send all of the reference angles and stuff like that. This is the main file, so this is the setup and loops. I use a couple of loops here just to try and parallelize some of the tasks. One thing important to note here is the filter function. So the IMU gives us two kinds of values. It gives us the angular speeds for each of the axes, and it gives us the acceleration. Now, if we take we can find the actual angle by just knowing how much time has passed between each of the measurements that we get. So if we know the angular rate, if we know for how long that angular rate has been, so that's the sample time. For the IMU, we can calculate the actual angle, but there are some issues with that, like sensor drift, and so you use filters like Magwick, Kalman, and stuff like that. Won't go into stuff like this, but it's pretty easy to integrate using the Adafruit AHRS library, where you just call this, where you'll see the function calls, and you get the angles that you need. So let's go see that part now. That's the most interesting one. That's the controller one. So using the IMU object, we get the acceleration and the gyro values. But now using the filter, we can actually get the roll, pitch, yaw, and yaw rate. I mean, yaw rate is actually just from the IMU directly. And then we can apply what I've shown you in the drawing, or the 3 separate PID controllers. And then we can just do the calculations that you also seen for the motors. And these are just some additional things like constraining those variables that they're in a certain range and stuff like that. And also I've added an arm command so that when the drone is not armed, the LED is blinking green, and you know it's safe to touch the drone to work with the drone. And also when you reset the drone, so when the throttle is below 0 or when you disarm it, you want to empty all of the accumulators so that the drone just doesn't start flying to one side or something like that. So essentially that's the code. There's not much else to it. It's pretty much all based around the 3 PIDs that I've already shown you, and getting those values to the motors. So before we fly the drone, let's take a look at the CAD 3D printed and finally tested. This is the final drone, like the drawing you've seen. So this drone uses the bigger 8520 motors with the bigger propellers than in the previous models, and we have all of the electronics here in the middle with the camera lying down, which is not ideal, but for initial tests it will work. And this is just a repurposed battery from an electronic device that you can buy at pretty much any corner store. So with the software done, electronics done, and now the mechanics done, let's see how the final drone turned out. And here's our finished tiny drone. I'm really happy with how tiny I managed to pack it all. The only question now is, can it fly? We'll test it out, but as you've seen, I've shown you a lot of things that how you shouldn't do it, so don't go too fast, double check everything. It will be much easier than troubleshooting later and then pretty much chasing ghosts, both hardware and software. This green thing here, so I just added a small buck converter that converts the 12 volts from our boost to the 5 volts for the USB cable, and it's powering the drone like this, no problem at all, but doesn't look the prettiest. Still, let's go give it a test flight to see if we can at least do one successful takeoff. Before we begin, I just want you to notice all of the safety features, like the blanket on the wall that I pretty much put there with duct tape, as you will see, and the small anvil so that the drone doesn't fly into the wall. Now let's get to the part you were waiting and how you expect the testing to go. It was just crash after crash, but it seemed promising at points, as you can maybe see from the video. But at some point the hope started to rise, and I managed to get a few clips like this. Even though it's off camera, I was still so happy that it actually flew a bit. It's not much, but I was still so happy that it took off. The problem here was that all of those crashes didn't really do good. The drone and one of the motors just stopped spinning, as you can see here. And we actually had a few kinda successful liftoffs. I'll count it as half success, but as you can imagine, doing this, or something like this, doesn't go too well with the hardware, and I managed to damage something, of course. The motor itself works when you connect it to a power supply, but for some reason the board doesn't want to spin that motor anymore, so I'll need to troubleshoot the hardware again to see what has happened. But anyway, we still managed to get a few takeoffs from this. My goal with this video wasn't to just show you an end solution for you, like the multi-V or beta flight or something like that, where you can just put the software down the drone and off you go to fly. This was more of an educational take on making a drone, so going really low level, just using PWM signals and writing your own free PID controllers for flying the drone. And we actually managed to get it off the ground, with which I am more than happy. So if you're interested in trying anything like this, good luck. That's all I'm gonna say with this PCB, but I think I found most of the bugs by now. You can find all of the files, codes, CAD files, Gerber files for the PCB, everything down below in Element 14 community. If you have any questions or comments, please leave them down below, and until next time, see ya!